In this video, let's take a more formal, precise look at the idea of reducing one language to another language and look at some of the things we can prove with this technique. Our goal is to reduce one problem into another, and we have already used and introduced this notation here. Remember that problems are languages. Solving an instance of a problem is nothing more than determining whether a string is a member of a language or not. So a problem can be described is a language. So we can talk about reducing one problem into another problem, or more precisely, we can talk about reducing one language into another language. So we use this notation, looks like a less than or equal with a little m next to it, to indicate that language A reduces to language B. And we say that A reduces to B if there exists a function, and it must be a computable function, such that for every x, if x is a member of A, then f of x is a member of B, and if x is not a member of A, then f of x is not a member of B. I've drawn a picture here to try and show what we're talking about. Okay, each of these dots is a string. Okay, and these dots are either in language A or not in language A. Okay, these dots over here are either in language B or not in language B. So the reduction is a function, and it maps things that are in A to things that are in B. And it maps things that are not in A into things that are not in B. Okay, so if we look at these as languages, then these dots are strings. If we look at these as problems, then the problem of A over here has a bunch of different instances. Okay, and each dot represents a particular case of the problem or instance of the problem. These are the instances for which the answer is yes, and these down here are the instances of the problem for which the answer is no. And so a reduction exists if there's a function, or the reduction is the function, that has this property. So we're looking for a function that is computable. In other words, we can do it without looping infinitely, that will take elements that are in A to elements that are in B, and elements that are not in A into elements that are not in B. So here is what we have used this technique of reduction for so far. If A reduces to B and A is undecidable, then we can conclude that B must also be undecidable. Okay, remember, this is the acceptance problem for Turing machines, and this was the emptiness problem for Turing machines. And we reduce the acceptance problem to the emptiness problem. Okay, if we can find that reduction, then we can conclude that the emptiness problem is undecidable because the acceptance problem is undecidable. So if A reduces to B and A is undecidable, then language B is also undecidable. But we can use this technique in other ways as well, in the other direction. If A reduces to B, again, A reduces to B, and instead of A being undecidable, we know that B is decidable, then we can conclude that A is decidable. Okay, if you've got an algorithm to decide B, then you can create an algorithm to decide A. All you need to do is take a potential candidate in language A, run the mapping function to a string, and then ask whether that string is in B or not. And if that mapping reduction function exists, as we've described it, then if B is decidable, A is also decidable. We can also do this with recognizability, not just decidability. Okay, so we have a couple here to say that. Again, A reduces to B if A reduces to B. Okay, if A reduces to B and B is Turing recognizable, okay, then A has to be Turing recognizable. If we've got a particular element and we want to know whether it's in A or not, we can reduce it to an element and check that to see whether it's in B or not. If B is Turing recognizable and the element is in B, then our algorithm will eventually accept it and we'll know that yes, it was in A. So in that way we can show that how to recognize an element that's in A. And so if B is Turing recognizable and there's a reduction from A to B, then A is Turing recognizable. And in the other direction, if A is not Turing recognizable and we find such a reduction, we can conclude that B is not Turing recognizable. So these are the ways we can use this idea of reducibility to prove things are decidable or undecidable, Turing recognizable or not Turing recognizable.